Hello, everyone. You're welcome to class again. And today we are going to be looking at the topic generalized material balance equation, which is one of the major topics which you have to be acquainted with in your reservoir engineering. So quickly, we are going to be looking at reservoir types, the general material balance. There will be a recap on reservoir drive. We're going to be looking extensively at the Schutter's material balance assumptions, equations, and then lastly, the Avena and Ode derivations. Okay, so let's get right into it. As a way of reminding ourselves, reservoirs are generally classified into volumetrically controlled reservoirs and hydraulically controlled reservoirs. By volumetrically controlled, we mean there is no water drive. So because there is no water drive, the hydrocarbon volume is constant, the connate water saturation is equally relatively constant, and the reservoir pressure declines as production occurs because of depletion. And the reason for declining of the um, reservoir pressure is because there is no drive, especially from a water body, such as an aquifer, to maintain the pressure of the reservoir. So there is a decline in the reservoir pressure of the system, of the reservoir system. The connate water is equally relatively constant, and the hydrocarbon volume is constant as well. So in this case, usually it's a depletion drive. The reservoir is referred to as a reservoir that depletes with time because there is no water drive and it is volumetrically controlled. Secondly, we have reservoirs referred to as hydraulically controlled reservoirs. In this case, you have water drive, which maintains the energy of the energy of the reservoir system. And in this case, the reservoir pressure does not decline as fast as that of the volumetrically controlled reservoir. So in this case, the hydrocarbon volume is not constant because as production occurs, and then pores are left, pores which contains reservoir pore volume, which contains the hydrocarbon volume. As the hydrocarbon volume is produced, uh, water there is an influx of water from the aquifer, either from the aquifer or from natural source, okay, to replenish the pore volumes left by the hydrocarbon fluids. So in this case, the hydrocarbon volume is not constant. The reservoir pressure is fairly constant as production occurs, and this is because there is constant supply of energy from the aquifer, that's the water body. Okay, so and as well, the connate water saturation increases due to influx of water from the water body. That's the aquifer. So basically, we have the volumetrically controlled. There is no water drive, no water influx, and then the hydraulically controlled, in which you have the presence of energy from the water drive. Okay, so for the generalized material balance equation, at times is as G representing generalized and MB as the material balance equation, but in most textbooks, you will see it generally has the MB, that's the material balance equation. In your reservoir journey, one of the things that you need to get acquainted with is the material balance equations, the basic equations which needs to be understood. The MBA was first developed by Schutter's in 1936. It is referred to as a zero-dimensional model with many applications. We're going to be seeing that in the course of the lecture. MBE keeps an inventory of all material entering, leaving, or accumulating within a region over a discrete period of time during the production history. So the major aim of the MBE, that's the material balance equation, is to keep all inventory of your reservoir fluids living or accumulating within the region of your reservoir. Okay, and then in 1963, Avina and Ode did an interpretation of the MBE, that's material balance equation, that was developed by Schultes. We are going to be looking at all that shortly. The use of the computer and sophisticated multidimensional mathematical models has, however, replaced the general material balance over time. So today we have multidimensional mathematical models which has been developed based on the material balance equation, and been used in the petroleum and gas industries. Okay, so what does the material balance equation state? It states that since the volume of the reservoir is constant, the algebraic sum of the volume changes of the oil, the free gas, the water, and rock volume in the reservoir must be zero. So what this is saying is that the sum total of the volume changes of the reservoir fluids. Basically, you have three basic reservoir fluids, which I believe you know that already. You have your oil, your gas, the two basic ones, and then you have a presence of water as well. Okay, then the rock volume present in your reservoir. The algebraic sum of the action of these three, okay, must be zero. For instance, you have decrease in oil and gas as it is produced from the reservoir. What happens? This must be balanced by an equal magnitude of responses of the water and the rock volume. Okay, so the MB is an equation based on the, okay, just a minute. The MB is an equation based on the application of the conservation of mass. Conservation of mass, matter can neither be generated or destroyed. So you have the algebraic sum of all these fluids and the action of the rock itself, the reservoir rock itself, being summed as zero. We're going to be seeing that shortly. Okay, so why is MB referred to as a zero-dimensional equation, a material balance equation? Why is it zero-dimensional? Okay, zero-dimensional because reservoir is considered as a single tank or region that is characterized by homogeneous rock properties. So for this, one of the major assumptions in MB is that your reservoir is an homogeneous, considered to be homogeneous. Okay, considered to be as homogeneous rock properties, let's say in terms of the porosity, the permeability. It is assumed that these properties are homogeneous across the reservoir. Okay, that's one of the major assumptions in MBE. The reservoir is described by an average pressure, that is, no pressure variation throughout the reservoir at any particular time or stage of production. So also in the material balance equation, the assumption is that there is an average constant pressure across your reservoir, that there is no pressure variation, okay, throughout the lifetime of a reservoir. So these are the major assumptions. I want to take note of them. Number one, that is a homogeneous rock property is assumed across your reservoir, and then the average pressure is also assumed across your reservoir at any particular stage of production. Okay, so let's look at the uses of generalized material balance equation. Usually used to estimate the stock tank oil initially in place, that's your OIP, and the free gas initially in place. I'm sure you're familiar with this now. Your oil initially in place, that's your N, and the free gas initially in place, that's your G. Okay, that's your hydrocarbon volumes in place. It's also used to predict the rate of water influx. You'll be seeing that as you go on in your reservoir journey. Water influx from the aquifer to the reservoir. Okay, to predict reservoir pressure, to predict presence of gas cap. If the gas cap is present in your reservoir or not, you can use the MBE, okay, reservoir pressure as well, to determine possible extension of the reservoir that is partially appraised or developed. So you can use your MBE to determine whether it is possible to extend your reservoir, okay, and also to appraise it based on the production that is ongoing. Also, to predict future reservoir performance, can we increase production? Does our reservoir have a higher capacity to produce more, or is there going to be a decline? So, to produce the future performance of your reservoir. So, MB makes all these possible. To also predict the ultimate hydrocarbon recovery under various types of drive mechanisms. So it can tell you the hydrocarbon recovery under various types of drive mechanisms, which we have discussed before now. the drive mechanisms we have discussed before now. Okay, so let's go on. Um, the general material balance assumptions. Okay, so I've said a little about this, but here we can see the assumption, basically the reservoir characteristics, like I earlier mentioned, that the reservoir has uniform porosity, permeability, thickness characteristics. So in addition, the shifting in the gas oil contact or oil water contact is uniform throughout the reservoir. So you know your GOC, that's the contact between your gas. There is the presence of a gas cap and your oil. And your oil water contact, that is the contact in between your oil and your water. You see this as we go on. So the reservoir has a uniform property. It is assumed that across your reservoir, okay, all the properties are uniform. And secondly, the fluid recovery is considered independent of the rates, the number of wells, or location of the well. So this is also one of the assumptions in material balance equation, that no matter where the well is positioned, the location of the wells, the number of the wells, fluid recovery, reservoir fluid recovery can still be ongoing, independent of the number of wells and location of the wells, and equally of the rates of production. Okay, and then thirdly, pressure equilibrium. All parts of the reservoir have the same pressure and fluid properties, and therefore constant throughout. So it's also assumed that there is an equal pressure. Okay, there is a pressure equilibrium, meaning that an average pressure of the reservoir um, is constant throughout the reservoir, and equally the fluid properties, the reservoir fluid properties, your gas and your fluid, and your oil, the properties are equally relatively constant throughout the reservoir. And then lastly, the constant reservoir volume. I mentioned this earlier. Reservoir volume is assumed to be constant except for those conditions of rock and water expansion or that of water influx that are specifically considered in the equation. So we'll see this as we go on. I want you to take note of the material balance assumptions. Very key. The reservoir characteristics, the fluid recovery, the pressure equilibrium, and the constant reservoir volume that you have across your reservoir. Okay. So in developing the HEMBI material balance equation, you need some laboratory data. Let me also mention that text used for developing this class, you have your DEX, you have Tariq and Ahmed. So all these texts are equally available to you. You can have them and then check out the topics in this text. You can equally use other good reservoir engineering textbooks. Okay, so let's go on. Laboratory data needed for the development of MB. You need your initial reservoir pressure and the average reservoir pressure as successive intervals after the start of production. So there's the initial reservoir pressure, the pressure at which your reservoir force exists, and then the average reservoir pressure. As production goes on, there is a drop in pressure. Sometimes the drop in pressure is minimal. Sometimes you have a large drop in pressure. So the data of your drop in pressure okay, is needed. Secondly, the stock tank barrels of oil produced is that's in STB at the surface, measured at 1 atmosphere and 60 degrees Fahrenheit. I'm sure you know that 1 atmosphere and 60 degrees Fahrenheit is standard conditions. Okay, at any time or during any production interval, that's in terms of pressure, as pressure drops. And then thirdly, the total standard cubic feet of gas produced. So as you need the stock tank barrel of oil at standard condition data, you also need the total standard cubic feet of gas produced. That's the oil produced and the gas produced at SCF. So I believe by now you know that your gas is measured in SCF and your oil at the surface is measured at STB, in STB. So when gas is injected into the reservoir, this will be the difference between the total gas produced and that returned to the reservoir. So in cases where you have production of gas from a reservoir and then you are injecting part of this gas back into the reservoir, so your total gas produced, the gas the difference will be in between the total gas produced and the one returned to the reservoir. So the gas you have at the surface will be the total gas produced minus the gas you injected into the reservoir. Okay, and then fourthly, you need the ratio of the initial gas cap volume to the initial oil volume. That's your free gas volume to your reservoir oil volume. That's your gas cap size. Okay, your hem is your gas cap size. So we'll see this as we go on. So these are the laboratory data that is needed for development of MBE. Okay, let me also mention that the other PVT data that is also needed, your HARES, all these need to be, your HARES as your solution gas oil ratio needs to be measured. So you have different experiments that can be carried out in the laboratory on your oil, samples of oil that is taken from the reservoir. You have the flash separation and the differential separation of gas, by which you measure the solution gas oil ratio. So you can read up your flash separation and your differential separation, which can be carried out in the laboratory. Okay, so for your flash, basically, as you drop pressure, you subject the samples of oil taken from the field, you subject it to reservoir fluid conditions in the laboratory, and then as pressure drops, there is evolve of gas from your oil. So if the oil is left in contact, if the gas evolved is left in contact with the oil, that is a flash separation. While if the gas is driven off, okay, from the oil, that is the gas is removed from the oil as pressure drops, that's differential separation. So you can check up text to know the difference between flash separation and differential separation, which occurs which is carried out in the laboratory in order to obtain your solution gas oil ratio data, the solution gas oil ratio data, and other PVT data that are equally needed in your MBE, development of your MBE, material balance equation. Okay, so let's go on. You remember that the overall performance of oil reservoir is largely determined by the nature of the energy. That's the driving mechanisms, okay, available to drive your oil from the wellbore to the surface. So basically, you have your rock and liquid expansion drive, your depletion drive, that's your solution gas, can be your solution gas, your dissolved gas, your internal gas. Usually, sometimes you refer to this as the solution gas. So you also have the gas cap gas drive, the water drive, the gravity drainage drive, and then you can have combination of these drives. Combination of this drive. You know your water drive, you can have the strong water drive, weak water drive, and the partial water drive. Your gas cap drive, there's the energy from the gas cap. Your solution gas drive is a depletion drive, because as gas evolves from the oil as a result of pressure drop below the bubble point, you have depletion of such drive. Okay, initially could be high, but as production goes on and there's production of both gas and oil from the reservoir, the energy from that solution gas, okay, depletes with time. Okay, and then you have your gravity drainage drive, and then combination drive. So let's see this in a moment. Here is the solution gas drive. Solution gas drive. Here at the top here, you see the oil producing wells. Initially here, you see your oil. Okay, this is the original condition. As production goes on, what happens? This is 50% depleted. You can see that the contact has gone higher. And then you have bubbles of gas. You also can see bubbles of gas also within the wells. This is the solution gas. So the energies of the solution gas drive the oil to the surface. Okay. And here you have the gas cap drive reservoir. Okay, this is the gas cap here and a map view. This is the gas cap and this is the oil zone. So as expansion of the energy of this gas cap occurs, what happens? It drives this oil to be produced to the surface. And what you have here, the cross-section view, you have this gas cap. So this is gas oil contact. This contact here, the line you have here, is the contact between the gas and the oil. So this goes down gradually, expands gradually as the gas expands. You have production of oil to the surface. So this is the energy of the gas cap. Okay. And here you have also the gas cap drive. Okay, so here you can see the gas and the oil here. Here you have the gas oil contact. Okay, so this is the initial gas oil contact. The contact is the line in between your gas and your oil. Okay, so here is higher here. I have your wells drilled here into your oil zone. Your oil zone is also referred to as the pay zone. So when you hear pay zone, that's the oil zone. So the gas, as the energy of the gas cap, okay, what happens? The gas expands because it's highly compressible. And then you can see the gas oil contact has moved here. And as a result, you have production of oil in this zone, okay, in this zone. So with time, this well will likely be abandoned, as this well 2 and well 3 further produces oil from the energy of the gas cap. Okay, and here you have your aquifer geometries, aquifer geometry from the water drive. You can have the linear aquifer, the edge, linear water drive, edge water drive, and the bottom water drive. Okay, so for the edge water drive that you have here, the water flows radially into the reservoir. Okay, flows radially and vertically. Okay, for here, for the edge water drive, water flows radially into the reservoir, driving the energy of the reservoir for the production of the reservoir fluids to the surface. Here, vertical direction of flow of water is negligible. Okay, so for the bottom water drive, the flow is both radial and vertical. So here you have bottom water drive. Can you see the aquifer underlying your reservoir, fully underlying your reservoir? So this is the water body. So here you have both radial and vertical flow of water, inflow of water or influx of water into your reservoir. And for the linear water drive, so flow is from one flank of the reservoir. Okay, this is the oil reservoir. You only have the aquifer attached to this flank of the reservoir. So here flow is strictly linear with constant cross-section area. Flow is strictly linear into the reservoir. So just for you to know that when there is presence of an aquifer, your reservoir, like have under the reservoir drive mechanisms, you can either have it as linear, as edge water drive, or the bottom water drive. Okay, and you can also have artisan, the artisan water drive. Okay, you can either have water drive as a natural water drive or an artificial water drive. So in this case, it's also, can also be considered as natural because there is an outcrop, and from this outcrop connecting to your reservoir, there is flow of water from the surface. So for an artificial water drive, the water flow usually come from the surface. Here there is an outcrop of sand. Okay, from it, water, you can see water here. Let's say there's a rain, and water flows directly, okay, forming a water body underlying your reservoir and driving your oil well. So sometimes there is connection to the surface where you have water flow. So that is regarded as artisan water drive. Okay, so in cases where you have combination drive mechanisms, here you have the gas cap here, and then you have the oil zone. So here you can have expansion that occurs within your oil zone, your solution gas expansion, and then the expansion from your gas cap. So what am I saying in essence is that there could be a drive as a result of your compression of the gas in your gas cap, and then um, the expansion of the gas, solution gas within your oil zone. So both can drive your reservoir. So in that case, you have a drive mechanism, combination drive mechanism from the gas cap and equally from solution gas within the oil zone. Okay, so let's also look at cross-section of combination drive mechanisms which we can have. Combination drive mechanisms which we can have. So you have here, you have your aquifer. You can see your aquifer. Underlying your reservoir is your oil zone, and then you have your gas cap. So you have the water body, you have the oil zone, and you have the gas cap. So we have wells that are located here, located all wells located within the oil zone, Okay, the oil zone extends from here to here because this was the original gas oil contact and this was the original oil water contact. That is the contact between your oil and your water. Okay, and here you have the contact between your gas and your oil. So here for these two wells, you can have the oil gas cap gas and solution gas. You can have the drive from your oil, drive from the gas cap gas, and drive from the solution gas. So from the expansion of your oil, energy from the expansion of your oil, the oil zone, energy from the expansion of your solution gas, and then energy from the gas cap can drive oil for production in these two wells. Remember that these two wells are closer to the gas cap. Okay, so you expect that the energy from this gas cap will drive them. The energy from the oil expansion and then the solution gas will equally drive oil. Okay, so here you see this dashed line. So this is a new gas oil contact. Okay, as gas expansion occurs, what happens? This contact moves down. It moves down. Okay, so here we see these two wells located directly in the oil zone. So here you have energy from the oil and energy from the solution gas. Okay, this is quite a distance from this gas cap. So, or assuming that in this zone, there is no presence of gas cap. Okay, so you have energy within the expansion of your oil and the solution gas. Expansion of oil and the solution gas. Okay, those are the two energy drives, okay, for these two wells. And here you have your oil, you have the solution gas, and you have the energy from the aquifer driving these two wells. Energy from the aquifer, okay, as production occurs, what happens? This aquifer responds. It responds by sending influx of water to replace, your oil is located in the microscopic pores within the reservoir. So as the oil is produced from the microscopic pores, the pores are left empty. So there's a drop in pressure. What happens? Your aquifer responds by influx of water into the pores of that reservoir, thereby balancing the pressure within the reservoir system. So in that case, we say if this aquifer is a strong aquifer, okay, I'll still tell you what a strong aquifer, a weak aquifer, and a partial aquifer, what it means with time. Okay, so if it's a strong aquifer, for instance, you have the flow of water into this reservoir. The rate of flow is quite high. You have it replacing the empty pore volumes left by the oil, production of oil, as fast as possible, such that you have balancing pressure between your aquifer and your oil zone. So thereby you maintain pressure, and then there is production of your reservoir fluid to the surface. So you see that the energy driving these two wells quite different from the energy driving these two wells and quite different from the energy driving these two wells. So you have to know why is there a difference between this, and this. There's a similarity between all these 6 wells, and at the same time, you have the differences because of their location and proximity to the drives that are present within the reservoir system. Okay, so we have also spoken about gravity drainage, reservoir, whereby you have a production of gas from your oil, and then the effect of flow of your gas as a result of differences in densities. Okay, difference in density between your gas and your oil. Your oil is quite heavier than your gas, so your gas flows upwards, forming a secondary gas cap. So in cases like this, you may not even have a primary gas cap or gas cap of um, natural gas cap of that reservoir may not exist. So in this case, the gas evolving from this oil, okay, forms a secondary gas cap. And then as the gas pushes towards forming that secondary gas cap, the energy of it and its expansion as well, okay, and its expansion as well drives the oil, okay, because of its heavier density towards the wells. And the locations of the wells are equally important. Okay, so drives the oil towards the wells, and you have production of reservoir fluid to the surface. So producing well located on low on structure is low on structure because we want to use this gravity drainage reservoir drive, okay, in producing this well. So oil flows down while the gas flows up. So it is intentional that the wells are located on low structure. Okay, I hope we can grab that. So quickly, let's use our times used in the general material balance equation adopted by Society of Petroleum Engineers. So I'll take a break here and I'll see you in the second part of this video.